Hello APC Mechanics students in Unit 2 Newton's Laws of Motion, Class 8 Atwood's Machine, Part 2. Then Section 1 Modified Atwood Machine Horizontal Support. In today's video, we're gonna see some modifications on the previous Atwood machine that we have introduced in Class 7. Consider the following Atwood machine: massless pulley and massless and extensible cords. Now at this stage, we know what is the importance of the pulley to be massless, because tension will be transmitted at the edges of the pulleys the same. The cords to be inextensible in order for the tension, and massless in order for the tension to be equally submitted along all points of the cord or the rope. Here in this case we have two masses, one of them lies on a level surface and the other hangs freely. The modification that we have done is that one of the blocks slides on a horizontal frictionless level surface. We have no friction. The aim of this section is to determine the acceleration of the system in terms of mm and physical constants as appropriate, and this is done using a big law, which is Newton's second law. But remember that we need to determine the tension in each string, the expressions, we need to equate them, then find the acceleration of the system. Now remember that the architecture in approaching Atwood problems is to determine the tension in each string and equate to get A. So first let's determine, or let's consider the FBD of block M. We have the pull of gravity down, the normal push is up, they are balance forces, and we have the tension along the string pointing away from M to the right. So now we can apply Newton's second law. Pull of gravity and the normal push are 0. Then the tension is MA, so the first expression of the tension is given by that. Now let's apply the FBD. So first let's set up the FBD of block M. We have the pull of gravity down, the tension is up, and notice that the pull of gravity has been represented by length greater than that in order to indicate that it's accelerating downward. Now let's apply Newton's second law, considering the fact that down is positive, so that would be mg minus ft is ma. And ft, if we isolate it, taking this to the right hand side, this to the left, then ft would be mg minus ma. Then equating the tension force and solving for A, we have two expressions for the tension, this one and this one. Now we can equate them together, and we need to solve for A. So dragging this to the left hand side and factoring out A and dividing by the total mass, then the acceleration of the Atwood machine, or the acceleration of the masses, is given by that. Now before I refer to section 2, let me do an interpretation for this expression. So after the derivation, we have determined that A is given by capital M divided by total mass multiplied by G. As we always do, we expect the expression of the acceleration to be a fractional mass multiplied by G. In the numerator, we expect to have an algebraic sum between different masses. But here y, small m, doesn't appear in the numerator because its motion occurs on a level surface. It's not hanging freely, it doesn't have any vertical motion. For this reason, we understand this by saying that m doesn't oppose the motion in any sense. So it's neither helping nor opposing. For this reason, the numerator would be absent, it doesn't include m. However, in the denominator, it will be included, because this would increase the inertial mass of the system. Okay, so it will be absent from the numerator, but it will be present in the numerator in the absolute sum. Now section 2, modified Atwood machine inclined plane. Consider the following Atwood machine: massless pulley and massless and extensible cords. The modification that we have done is that one of the blocks slides on a frictionless lamp. The aim of this section is to determine the acceleration of the system in terms of mm and physical constants as appropriate. This can be done using Newton's second law. We are not pretty sure whether the system will accelerate along m or m. So here, in this case, even if this is greater than that, or vice versa, we're not pretty sure the direction of the acceleration, because there is another factor that have entered the game, which is theta. Now we will suppose it will accelerate along capital M, and the final result will be interpreted later. So we will suppose that small m will accelerate up the incline and capital M will accelerate down the incline. Remember that the architecture in approaching Atwood problems is to determine the tension in string and equate to get A. So the FVD of block M, and notice that the FVD of the block along the incline have represented by a shifted X and Y. So we have the pull of gravity down, we have the normal push up, we have the tension up the ramp, and remember that this is used to utilize Newton's second law. So the different forces acting on the block M is given by the pull of gravity, normal push, the tension, and MA. Now considering that the positive direction along the ramp, the positive is the direction up the ramp, and mg makes angle theta with the y-axis. So now we're ready to project this vectorial equation. Now mg would be in the negative direction, that would be mg cosine theta, and this component would be minus mg sine theta. So plus the tension force, which is ma, and remember that we're searching for ft. Isolating ft, that would be ma plus mg sine theta. So this is the first expression of the tension. Now we need to determine the second one, and this can be done by utilizing the FVD of capital M. We're supposing it's accelerating downward due to gravity. Tension is holding it up, and now we can apply Newton's second law. Small m would be replaced by capital M because this is the mass of the block. Now projecting it, so here it should be along the horizontal, along the vertical, and down is positive because it's accelerating downward, that would be mg minus ft, which is ma, and isolating for ft, taking it to the right hand side and this to the left hand side, that would be the tension is mg minus ma. And now we have the second expression of the tensions. Now we're able to equate them. In order to solve for A, ft is ft, then ma plus mg sine theta is capital mg minus capital ma. So the acceleration appear in two places. We need to drag this to the other side and this to the other side, and we're left with that. Factoring out A, dividing by the total mass, then the acceleration of such configuration is given by that. Now section 3, interpretation for a modified Atwood machine massless pulley. So here I'm referring to the first configuration that we have done. The acceleration is given by m2 divided by the total mass times g. In the numerator, the mass m1 on the horizontal support vanish, since it's neither helping or opposing the motion, as I have stated previously. Now what about the inclined ramp? The acceleration is given by m2 minus m1 sine theta. In the numerator, the mass m1 on the ramp is suppressed by sine theta. So this, okay, so we're supposing here that this is moving down, this is moving up. So this is helping the motion, it's preceded by plus sign. This is opposing the motion, it's preceded by minus sign. But we need to make the modification and multiply by sine theta due to the inclination of the ramp. So any mass that slides partly vertically along a ramp inclined by theta, the modification that would be done in the numerator, that it would be multiplied by sine theta. To determine whether the system will accelerate along the mass of the ramp or the mass that is hanged freely, so here I'm saying that in order to determine whether this will accelerate like that or like that, we need to compare not m1 and m2, but rather m1 sine theta and m2, because in the numerator this and that will appear. m2 will appear solely without any trigonometric functions because it hangs freely, while m1 will appear suppressed by sine theta to compensate for the vertical component. If m2 happens to be greater than m1 sine theta, then the system will accelerate along the direction of the hanging mass, and the acceleration in this case is given by that. That would be the magnitude of the acceleration. However, if m1 sine theta is greater than m2, then the system will accelerate along the direction of the mass on the ramp. So it will accelerate like this, and the acceleration would be expressed as m1 sine theta minus m2. Why we have flipped the signs? Just to make sure that our acceleration as a value would be positive. Now for a modified Atwood machine massless pulley, the acceleration of an Atwood machine with a double ramp is given by, so suppose we have, let me draw it here, suppose we have a double ramp like this. So suppose here we have a pulley, here we have a certain mass, and here we have another mass. Suppose this is inclined by alpha, this is inclined by theta. So how know that this is the mass m2 according to this expression? Because m2 is related to alpha, then this is m2 and that would be m1. The acceleration in this case would be given by m2 sine alpha minus m1 sine theta divided by the total mass multiplied by g, and the system will accelerate along the greater mass suppressed by sine of the corresponding angle. The denominator always and forever holds the sum of masses independent of which version of Atwood's machine. So if you consider all three configurations, whether level surface, ramp, or a double ramp, the denominator would be the total inertial mass. So we're done with that. Now let's start with the exercises. An experiment is set up using a hanging mass to pull a cart along a horizontal track. A light string is attached from the hanging mass over a pulley to a force sensor. A second light string is attached from the force sensor to the cart. So here we have a cart that can move on a level surface. From this cord we connect a force sensor, so this force sensor is measuring the tension along this cord, and from the other end we connect a cord that passes through the groove of a pulley, and we have a hanging mass. There is a motion sensor that can be used to measure different features of the motion of the cart. The pulley is ideal, this is important, which means that all previous argumentations here work perfectly, and there is negligible friction between the cart and the track, so friction here is neglected. The cart of mass m starts at rest, so the initial speed is 0, and we suppose that we're gonna start from the origin. This can be always reset based on our preference. The reading on the force sensor is F, so the force sensor is measuring a force F, which is basically equal to the tension in the string. Which of the following is a correct expression of the distance that the cart moved in time t? So the distance is basically the position and given by the kinematic equation or equation of motion. Now, why I have used this equation? Because we suppose that this force that the force sensor is measuring is constant, because they told us it's just F. So we're allowed to use this equation. We're starting from the origin, starting from rest. Then the distance, which is x, is given by half ax t squared. Notice that the choices are expressed in terms of time. Now, but we don't have acceleration, we have the force. Now, acceleration can be related to the force using Newton's second law. We'll apply that for the cart. Then what is the FPD of the cart? We have the pull of gravity down, we have the normal push is up, and we have the tension along the cord, which is basically the force F measured by the force sensor. Now, Newton's second law is given by F net is ma, the mass of the cart is capital M. Now we have the pull of gravity, the normal push, the tension in the string, this is equal to ma. So if you consider the horizontal direction, that would be 0 plus 0 plus capital F, which is ma. So basically the acceleration would be given by F divided by m, which is the acceleration along the x-axis, and that would be replaced by half F divided by m multiplied by t squared, which is ft squared divided by 2m, and in this case the correct choice is given by D. Now exercise 2. An experiment is set up using a hanging mass to pull a cart along a horizontal track. A light string is attached from the hanging mass over a pulley to a force sensor. A second light string is attached from the force sensor to the cart. There is a motion sensor that can be used to measure different features of the motion of the cart. the pulley is ideal and there is negligible friction between the cart and the track. So basically we have the exact perfect configuration that we have done in exercise 1. The hanging mass is released. Which of the following sets of graphs could represent output from the motion sensor and the force sensor? So we know that the acceleration of such configuration based on the type of the pulley and we don't have friction is given by A, which is a fractional mass multiplied by G, which means that A would be constant, which means the force exerted on the cart is constant. So force is constant, then it's either A or D, so we can directly eliminate these. And knowing that if the force is constant, acceleration is constant, which means the velocity is linear, then the correct choice would be D. Now exercise 3. In the system of 2 blocks and a spring shown above, blocks 1 and 2 are connected by a string that passes over a pulley. The initially unstretched spring connects block 1 to a rigid wall. Block 1 is released from rest, initially slides to the right and is eventually brought to rest by the spring and by friction on the horizontal surface. So okay, block 1 initially okay, so what's happening here is that after we do this configuration, block 1 will slide to the right under the action of block 2 due to the pull of gravity. The spring will bring it back and finally it will reach a point where it is at equilibrium, becomes at rest, so brought to rest by the spring and friction on the horizontal surface. So while it's moving left and right, friction will be acting on the block left and right based on the direction of motion. After block 1 comes to rest, the force exerted on it by the spring must be equal in magnitude 2. So after it reaches the rest point, they're discussing the force. Okay, they're telling us after block 1 comes to rest, the force exerted on it by the spring must be equal in magnitude to what? Now what will be the forces acting on block 1? We have, so I won't represent the forces here, but I will list them. We have the tension in the spring, let me say force of the spring. We have the tension in the cord, which is F tension, and there will be the force of static friction. So we have 3 forces, and we know that these 3 forces must be balance forces in order for it to be at rest. So if you refer back to the statement, the force exerted on it by the spring should be balanced by Ft and the friction, and in this case the correct answer would be C, the vector sum of the forces on block 1 due to friction and the tension in the string. So we know that it's not 0. In order for it to be at rest, these 3 forces must be balance forces. It's not friction alone, weight doesn't play any role. Similarly for E, so C would be the correct choice. Exercise 4. Block A of mass MA is on a horizontal table of negligible friction. A light string is attached to block A, extends over an ideal pulley, and is attached to block B of mass MB, which is hanging off the table as shown in the figure. When the 2 blocks are held at rest, the tension in the string is MB multiplied by G. The blocks are then released from rest. Which of the following is the correct expression for the new tension in the string while both blocks are moving? Now we know that for such type of configurations we can directly write the acceleration of the system, which is a fractional mass multiplied by G. In the numerator we would have the inertial mass given by MA plus MB, and in the this is in the denominator. In the numerator we're gonna only have MB, which is the mass helping the system. This is for the acceleration. If we need to determine the tension can be determined either by referring to this to A or to B. Let me try and refer to A. So for A, what are the forces acting on A? We have the pull of gravity, the normal up, the tension to the right. So if we apply Newton's second law, F net is M multiplied by A, that would be the pull of gravity, plus the tension, plus the normal is equal to the mass A multiplied by A. If we project it along the horizontal, that would be 0 plus 0, plus the tension force, which is equal to MA multiplied by A. So this is MA multiplied by A, and that would be MA multiplied by MB divided by MA plus MB multiplied by G, factoring out the fractional mass. So the correct expression in this case would be D. Exercise 5. Students attach a light string to a cart. The string passes over an ideal pulley. So the pulley is ideal, which means we can use all any argumentations that we have done previously to a hanger. A number of small identical plates are on both the cart and the hanger. The students measure the acceleration of the cart when the cart hanger plate system is released from rest. The students repeat the procedure for several trials. For each trial, students move one plate from the cart onto the hanger. So here we have number of plates, and here we have a certain number of plates. So we're gonna repeat the experiment by removing one plate being placed on the cart to the hanger. For each trial, students move one plate from the cart onto the hanger. The data collected and shown in the straight line graph, which quantities on the vertical and horizontal axis respectively could produce the graph shown. So if you look at the choices, we're trying to use the acceleration of such a system in order to get a straight line from the best fit line, and we know that a curve is a straight line whenever the slope is constant. So basically, for such modified Atwood machine, the acceleration is given by fractional mass multiplied by G. Here we have a fraction. In the denominator, we will write down the masses, all the masses given by the mass of the cart plus the mass of the hanger. And in the numerator, we will only place the mass of the hanger. Now, if you look carefully here, suppose initially we started with 3 and 3, then we removed 1 from here, then here we have 2, here we have 4, then we remove another 1, then we have 5, 1, and we have 5. If you notice that upon moving one plate from here to the hanger, the total mass given by the mass of the cart plus the mass of the hanger, which is given by the number of plates, remains constant. Then basically that would be constant and that would be constant. Then we can rearrange the expression and write it as G divided by MC plus MH multiplied by MH. And indeed, in this case, MH is varying, it is increasing because we're increasing the number of plates, and that would be perfectly constant because G is constant. Now this is in the form of y is equal to ax, which gives us a straight line variation of straight line with a constant, or straight line which means a constant slope. So in this case, the correct answer would be A. Along the vertical axis, we will plot the acceleration, and along the horizontal, we will only plot the total mass of plates on the hanger only. Now exercise 6, a block of mass M1 on a horizontal table is connected to a hanging block of mass M2 by a string that passes over a pulley as shown above. The acceleration of the block is 0.6 g, so we know that A is 0.6 g. Assume that friction and the mass of the string are negligible, and also we'll assume that the pulley is ideal. We need to determine the ratio M2 over M1. So this ratio can be determined by referring to the acceleration of the system, which is given by the fractional mass. In the denominator, we would have the inertial mass. In the numerator, we would be having the helping mass multiplied by G. Now A is 0.6 G, which is given by M2 divided by M1 plus M2. G with G would cancel, so we have 0.6 multiplied by M1 plus M2, which is equal to M2. So that would be 0.6 M1 plus 0.6 M2 equals to M2. So 0.6 M1 equals M2. 1 minus 0.6, after we remove this to the other side, that would be 0.6 M1 equals 0.4 M2. Then if we're searching for M2 over M1, taking this down and this down, that would be 0.6 over 0.4, which is 3 over 2, and that would be 1.5. And remember that all quantities in physics must have a unit. This is a ratio, and the ratio doesn't have an unit because kg would cancel with kg, and the correct answer in this case is D. Now, exercise 7. A block of mass m1 on a horizontal table is connected to a hanging block of mass m2 by string that passes over a pulley as shown above. The acceleration of the block is given by 0.6 g. Assume that friction and the mass of the string are negligible. We will assume also that the pulley is ideal. We need the tension in the string. If you refer to the choices, they're expressing the tension in terms of m2. So I will consider this block m2. Now, what are the forces acting on m2? We have the pull of gravity down, the tension is up. Now, the difference between the pull of gravity and the tension is equal to the mass times the acceleration, and this can be done using Newton's second law. F naught is ma. We have the pull of gravity plus the tension equals to m2 multiplied by a, taking the positive direction to be down. That would be m2g minus the tension, which is up, is m2a, and we're searching for the tension. So if we take this to the right and this to the left, that would be the tension is m2g minus m2a, and that would be m2g minus m2. The acceleration is given by 0.6 g. Now we can factor out g with m2. That would be m2g. Here we don't have anything, so we're left with 1 minus 0.6, and that would be 0.4 m2g, and the correct expression in this case is B. Exercise 8. As an exit ticket for today's video, a block of mass m1 is connected by string to a sphere of mass m2. The block is on a frictionless plane inclined at an angle of 30 degrees as shown in the figure above. The string passes over a pulley of negligible mass and friction, so the pulley is ideal. We can use all the previous argumentations, and the sphere hangs freely. Which of the following is always true if the block is accelerating down the incline? So we know that in this case, in order to determine whether it's accelerating along the vertical down or along the ramp down, we need to compare m2 with the modified mass, which is m1 sine 30. If m2 is greater than that, it will accelerate down along the vertical. If this is greater than m2, it will accelerate along the ramp down. So we need to accelerate down the incline, so m1 sine 30, so this should be 30. So that would be m1 sine 30 is greater than m2. And that's it for me in this video, guys. See you soon in a new one.